Athletes use smart devices like smartwatches to track their performance. At the heart of these devices are accelerometers, tiny sensors that measure acceleration forces and turn physical movements into digital data, providing insights into speed, acceleration, and detailed movement patterns. These accelerometers are typically MEMS-based sensors. Inside, tiny masses with plates on the sides are suspended by springs between a set of fixed plates. When the athlete moves, these masses shift, altering the distance between the plates. This change in distance affects the capacitance between the movable and fixed plates, which in turn alters the voltage level, generating a signal that corresponds to the movement. In traditional accelerometer applications, what we can call yesterday's technology, the analog signal first passes through amplification, filtration, and other conditioning circuits to enhance its quality before going through an ADC circuit, converting the prepared signal into a digital form. After that, microcontrollers or software are used to interpret these signals. This is ideal for applications needing continuous monitoring and data processing. However, many applications don't require the entire signal profile. They only need a straightforward outcome, like a simple on-off switch. The MEMS accelerometer switching approach changes how a typical accelerometer operates, enabling it to close a switch based on physical movement without complex processing. So, where in a typical MEMS accelerometer, the shift in the suspended mass generates an analog signal, this method takes a different approach. A physical stopper is added next to the movable mass. When a specific acceleration threshold is reached, the mass physically touches the stopper, effectively closing a switch. This turns the analog movement into a direct, binary response, removing the need for complex signal interpretation or additional processing. The applications of this approach extend beyond just acceleration. Similar methods have been developed for other sensors as well. For instance, in MEMS-based temperature sensors, a system allows a charger to automatically shut off when the temperature exceeds a set threshold, preventing overheating. Likewise, in pressure sensors, compressors are controlled by a switch that triggers when a certain pressure is reached. However, acceleration signals pose a different challenge. Unlike temperature and pressure, which have lower frequency and more static signals, acceleration signals are highly dynamic, prone to noise, random peaks, and external influences. As a result, relying solely on the signal's amplitude may lead to false triggers and unreliable system performance. To address this complexity, a more comprehensive approach is necessary, one that accounts for the signal's duration, sequence, and amplitude, ensuring a more accurate and reliable switching mechanism. To address this challenge, we developed a MEMS network composed of 3 interconnected units, M1 at the bottom, M3 on top, and M2 in the center. Each unit can be designed with different parameters for various applications. M2, being the largest unit, has the highest sensitivity to acceleration, allowing it to move first. The MEMS units are electrically coupled through parallel plates extending from each mass, with coupling plates labeled P3-2 between M2 and M3, and P1-2 between M2 and M1. With this, when M2 shifts, it impacts the other units, aiding their switching. Stoppers are strategically placed. M1 has its stopper below for downward acceleration, and M3 has its stopper above for upward acceleration. M2 features stoppers on both sides to enable switching in both directions. For real-time adjustments, we included additional parallel plates coupled with M2, called P2, allowing us to fine-tune its sensitivity by applying a DC voltage. The next image reveals an SEM view, a scanning electron microscope image, of our MEMS network, showing the detailed structure and design of all its components. In acceleration applications, both the amplitude and the sequence of the signal are crucial. The MEMS network can detect these sequences, such as the rising acceleration sequence and the falling acceleration sequence, and responds accordingly. Essentially, it acts like a smart switch, reacting to both the shape and amplitude of the motion. Here's how the system operates. First, we start by adjusting the voltage across the parallel plates to fine-tune M2 sensitivity. When the acceleration increases during the rising sequence, M2, the central mass, moves down in response. As the acceleration amplitude increases, M2 reaches the downward stopper and switches on. This movement decreases the distance between the plates of M3 and M2, increasing the electrostatic forces between the two, which influences M3 to shift upward. However, M3 doesn't switch on yet. It moves closer but waits for the falling acceleration to switch on. Next, when the acceleration decreases, M3 shifts upward in response, finally switching on. This switching indicates that it has detected the full transition from rising to falling acceleration. At this stage, M2 is expected to move upward during deceleration. However, due to hysteresis, which is similar to a memory effect, it remains latched in position. As a result, detecting M3 switching indicates the transition from rising to falling acceleration. In contrast, when we consider the other case of falling to rising acceleration, the opposite occurs. M2 switches up, M1 switches down, and M2 latches up. The system essentially functions as binary code. For example, you could say that 011 represents a rising to falling sequence, while 110 represents a falling to rising sequence. In real-life applications, these rising to falling and falling to rising signals correspond to human motions like sitting down and standing up. As illustrated, this system detects both amplitude and sequence. It offers 4 key features: high speed, low power, low cost, and adaptability, making it a powerful solution for numerous advanced applications across various industries. While one example is sit-stand detection, it can be expanded to identify other human motions like walking, running, or even falling, all with minimal adjustment to the system. This application can revolutionize devices like pacemakers, allowing them to adjust their functioning based on user activity. Due to its near-zero power consumption feature, it significantly improves battery life while doing so. Beyond human motion, another potential application is in automotive safety. With the near-zero latency feature, the system can be used with airbags, allowing them to trigger instantly during a crash, enhancing response time and accuracy, all with minimal adjustments to our MEMS network, as the crash produces a similar falling to rising acceleration sequence as the sit-stand case. Shipment quality monitoring is another potential application. To track the health of packages during shipping, our MEMS network could be embedded within packages to detect shocks and assess shipping quality during transit, ensuring product safety. This is made possible due to the near-zero power consumption and very low cost, allowing it to be used in important packages without significant additional costs. Furthermore, we can expand further. Our MEMS network is well suited for applications in robotics, industrial systems, medical devices, and automotive technology. By directly interpreting signal patterns without the need for an external computer, our 3-MEMS network represents the future of sensing technology, moving beyond traditional measurement methods. This is the next step in smart sensing. Currently, a 3-MEMS network can achieve all of this. In the future, we envision a larger MEMS network with hundreds of MEMS units, capable of tackling more intelligent applications, such as neural networks, analog computing, complex neuromorphic systems, and even smarter sensors.